So here are my ingredients. I have some water, some dish soap, cornstarch, a container that I'm going to mix it in, and some sand. This is my sand mixed with cornstarch, and I'm about to add the water. So for once, I think it actually worked. It might be a little soggy, but it feels really cool. Yeah, I think it's a little soggy. Let me go try to add some more sand. So as you can see, I added a ton more sand again because I really wanted to make it like work properly, but it's not working, even though I added another whole cup full of sand. So I think honestly it's because I really wanted it to work, so I put in a ton of soap into the water, and I think that's what's making it not work, possibly. But yeah, I wanted to let you know that I added a lot more sand, like a lot. It's very heavy, to really try to get it to clump and work, but it's not really working, which I'm not really gonna beat myself up for because it took that girl like a lot of tries with ingredients that weren't this. So yeah. This is my interactive advanced concept presentation 8, Kinetic Sand, and the last interactive advanced concept presentation. The materials for this experiment were sand, cornstarch, dish soap, and water. For the procedure, I mixed the sand and cornstarch. In a bowl, I combined some sand with 1 tablespoon of cornstarch. I stirred until they were well mixed. Then I added the water and dish soap. In a separate container, I mixed water with dish soap. In my case, I think I added too much dish soap because I was very eager to make it work, except I think this probably caused problems and didn't allow it to work. Then I stirred until the soap was fully dissolved in water. I slowly added the water and soap mixture to the sand and cornstarch mixture. I did a little bit at a time and would stir till it was completely gone, and I kept doing this. I stirred continuously to ensure even distribution of the liquid. Then I used my hands to knead the mixture until it reached a consistent texture. It should feel slightly wet but not overly sticky. However, in my case, it was probably overly sticky and a bit too wet. However, let's talk about what is happening in the reaction. Let's talk about polymers in action. Cornstarch contains a polymer called amylose, which is a long chain of glucose molecules. When water is added, these polymers hydrate and form a network that traps water molecules, creating a gel-like consistency. This interaction is similar to how kinetic sand behaves, maintaining a solid shape but flowing like liquid when pressure is applied. Cornstarch contains amylose, a polymer made of glucose units linked by, and I gave you the formula. When water is added, amylose hydrates, causing the long chains to unwind and interact with water molecules through hydrogen bonding. What is happening with the hydration and gel formation? The chemical reaction involved in the hydration of cornstarch, or amylose, can be represented as amylose plus H2O is amylose H2O. This creates a gel-like network that traps water, forming a viscous mixture. For the role of sand. Sand provides the granular structure that allows kinetic sand to flow and be molded. The grains are coated by cornstarch and water mixture, preventing them from fully compacting, which gives kinetic sand its unique properties. Sand, primarily silicon dioxide, acts as a granular base. The gel formed by the cornstarch and water coats the sand particles, preventing them from compacting too tightly. What about the dish soap as a surfactant? Dish soap acts as a surfactant, reducing the surface tension of the water. This helps in better mixing and binding of the ingredients. The soap molecules also surround the sand particles, adding to the fluidity of the mixture. Dish soap contains molecules with a hydrophilic, water-attracting head and a hydrophobic, water-repelling tail. These surfactants reduce the surface tension of water, enhancing the mixture and binding of ingredients. And I gave the equation. The surfactant molecules surround sand particles, further aiding in the fluidity of the mixture. So what about the physical and chemical changes? The process involves both physical and chemical changes. Mixing the ingredients physically combines them, while the chemical interaction between the water, cornstarch, and dish soap alters the properties of the mixture, transforming it into kinetic sand. The initial mixing involves physical changes, combining the ingredients. Hydration of amylose and interaction with surfactants involved chemical changes, altering the physical properties of the mixture. Let's quickly connect what we've seen to chemical kinetics and equilibrium that we saw in Module 2. The synthesis of kinetic sand involves principles of chemical kinetics and equilibrium. Chemical kinetics deal with the rates of chemical reactions and the steps by which they occur. In this experiment, the interaction between cornstarch and water, as well as the formation of the gel-like network, occurs over time, demonstrating how reaction rates can affect the final properties of a polymer. Equilibrium is reached when the forward and reverse reactions occur at the same rate. In the context of kinetic sand, the equilibrium is established between the formation of hydrogen bonds within the cornstarch network and the interactions with water molecules. The dish soap stabilizes this equilibrium by reducing surface tension, allowing for the unique flow properties of kinetic sand. In this experiment, I synthesized kinetic sand by combining sand, cornstarch, dish soap, and water. The cornstarch formed a gel-like network upon hydration, trapping water molecules, while the dish soap reduced surface tension, resulting in a material that behaves like both a solid and a liquid. This highlights the fascinating interactions between polymers and surfactants, demonstrating how everyday materials can be engineered for unique properties. This experiment shows the versatility of polymers and their potential for innovative applications. Thank you for listening, and thank you for a great semester.